Now next topic is interfacing. Okay, this interfacing also especially we are discussing here memory interfacing. See, see, interfacing means our microprocessor is connected with external devices. Let us assume this is our microprocessor. Okay, this microprocessor has, already we studied, internally it has address lines, data lines, some control lines and timing lines are there. Okay, so in microprocessor IO lines are not defined, right? And serial communication is only one communication is there, but synchronous, asynchronous, all these are not defined. Okay, then interrupt controlling also not defined, because interrupts are there, hardware interrupts are there, but externally memory location does not require only one interrupt INTR is there. If suppose more than the one interrupt occurs, more than the means more than the 8 interrupts occurs, then it does not accept the more than the 8 interrupts. So all these are some limitations are there. Okay, so connecting of all this purpose, it requires some interfacing devices. So interfacing devices main function is which connects the microprocessor to the external devices. So in that one basic external device I am taking here, IO device, input output device. Input output device is one example I am assuming keyboard. Okay, keyboard. So directly I want to connect keyboard to the microprocessor. Direct connection is not possible here because these are IO lines. In microprocessor, IO lines are not defined. That's why it requires one interfacing device. It requires one interfacing device. That interfacing device is also called as PPI, Programmable Peripheral Interface. Programmable Peripheral Interface. This purpose, one IC is used. That IC is 8255. Okay, so it takes the data from the input devices and same data is connected to the data lines here. See, any interface device is connected to the microprocessor through the data lines only. Data lines, again this data is connected to output devices like this through PPI only. PPI, Programmable Peripheral Interface, used to interface the input-output devices with a microprocessor. Right? Similarly, external interrupts. External interrupts. Right? So in 8085 microprocessor, internally it has 5 hardware interrupts. But if the number of interrupts are more than the 5 hardware interrupts, okay, if it is number of more than the 5 hardware interrupts, then we are using one controller, programmable interrupt controller. This purpose, one IC is used. That IC is 8259. Okay, 8259. It is also connected with data lines D0 to D7, and one request is there, INTR. INTR. Directly it is connected to the interrupt request, and the main function of this 8259 is it accepts the external interrupts and according to the priority, highest priority interrupt is connected to the microprocessor. Later one more interrupt, later one more interrupt. It performs like these operations. Okay, this operation purpose, interrupt controlling purpose, separate interfacing is there, 8259. Right? Similarly, sometimes we require serial communication. Okay, serial communication. So our data we require always serial. So in 8085 microprocessor, directly SID, SOD are there. Serial input data, serial output data. But sometimes we require the serial operation also. Different types are there. Serial communication, duplex, off duplex, full duplex, synchronous and asynchronous. All these operations we require. Right? That operation purpose, separate interfacing device is used. That interfacing device is also called as USART. USART. Universal Synchronous, Asynchronous, Receiving and Transmitting. Okay, this purpose, separate interfacing is used. That interfacing is 8251. Okay, 8251. This is also connected with data lines. See, all the interfacing devices are connected with data lines only, right? And one more application, timer applications. Internally directly timer generation is not possible, right? So that purpose here we required some timers ICs. This timer IC is 8253, 8253, which explains the external time period clock pulses. And one more operation is there, DMA, direct memory access. Direct memory access. This purpose separate IC is there, 8257. See, to perform any operation purpose, these are the general requirements. So input output device compulsory we have to connect. Sometimes external interrupts are there and sometimes serial communication. So these are the general requirement. And to perform all this operation purpose, externally all these interfacing devices are required. Okay, all these interfacing devices are required. This explains the interfacing, right? So 8251, 8255, 8259, 8257, 8253, all these are interfacing devices. Now memory interfacing, right? Memory interfacing, directly microprocessor is connected with the external memories. This is microprocessor, it is connected with external memories. To connect the external memory purpose, it has to perform first demultiplexing operation. Demultiplexing operation. So in this demultiplexing operation, your first device is latch is there. Latch. Okay. This latch is connected with ALE. This is address latch enable, which is used to demultiplexing of address bus and data bus. Okay. This is D0 to D7 and this is A0 to A7. ALE is 1. Then all these lines are acts as a address bus. Internally these are AD0 to AD7. And if ALE is 0, all these are acts as a data bus. And similarly, already we discussed, right? IO by M bar and read bar and write bar. These three are connected to one decoder. Okay, 3 to 8 decoder. It gives you totally 4 operations. What are those operations? Memory read. Next, memory write. IO read, IO write. So according to our operation, now these are the demultiplexing operations. This explains the demultiplexing operation, demultiplexing of the internal operations. Now we can connect all these lines to the any external devices. Now our topic is interfacing with memory. Okay, now here I am connecting memory here. Let us assume, I am assuming this is one memory, SRAM. Okay, this memory requires address bus and data bus. Data bus also required. Okay, sometimes chip select. Okay, this explains the chip select. Right, this is the general construction. Now I am taking separate diagram. See, this I am taking one memory. Okay, this memory standard representation is 2 power n by m. In this, this m explains the word length. It explains the word length. It depends on the data bus. Which data bus? M data bus it requires. And this 2 power n, this explains the memory capacity. Okay, memory capacity using how many address lines? N address lines. So using n address lines, the total memory capacity is 2 power n. So it requires address bus and data bus. Okay, this is data and this is address. How many address lines? N address lines. How many data lines? M data lines. You suppose SRAM capacity is 8 kilo by 8. Then number of address lines, okay, number of data lines. These things we require. See, I'm writing this 8 kilo. 8 kilo is in terms of 2 power n. 8 is 2 power 3. Kilo is 2 power 10. So total how much? 2 power 13. This explains the number of address lines. So how many address lines it has? 13 address lines. And this is directly explains the data bus. Okay, this explains directly data bus. How much data bus it requires? 8 data lines it requires. Address lines are 13 and data lines are 8. This explains the memory accessing capacity. Okay, so memory is always depends on the number of address lines and number of data lines. Now, one previous gate question I am taking here. 8 kilo by 8 SRAM starting and ending address is. Okay, 8 kilo by 8. So in this 8 kilo, 2 power 3. Kilo means 2 power 10. So totally 2 power 13. So it requires 13 address lines. So using 13 address lines, then starting address is always 0. Starting address is 0. So 13 zeros I am writing. Okay, ending address. In binary, what is ending address? Ending address should be 1 always. So I am writing all are ones. Right? Then address locations always we are to write in terms of hexadecimal format. Hexadecimal format, I am separating 4 bits. First 4 bits are separated. Okay, next 4 bits are separated. Then next 4 bits are separated. Then what is the location here? 0, 0, 0, 0, H. Next here location is 1, F, 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 H. Right? This is one procedure, finding starting and ending address. This depends on the number of address lines. So from the given memory, first we have to find out number of address lines like this, and from the number of address lines find the starting and ending address locations. Right? See, one more question is given. 8 kilo by 8 SRAM starting address is ABCDH. Then ending address is, see, in previous question 8 kilo by 8 SRAM is there. Starting address, ending address we are finding, but your starting address is mentioned. Like this is our complete memory, right? It starts with 000 and ending with some FFFH locations. Now at middle case some address is given. This is 8 kilo by 8. Right? The starting address of this one is mentioned. How much? A, B, C, D. Then what is this ending? We want this one now. For that purpose. Right? According to our analysis, just now I explained. So 8 kilo is 2 power 13. So using 13 address lines, the range is 000H2 1FFH. This is the range. Okay. Now the starting is starting address I am writing here. Starting address is ABCDH. Then ending address is, just add that location here. Perform addition of these two. After addition, it becomes here. See, After this addition, D plus F is C1 carry. Again D plus F is C1 carry. Again B plus 1 is C plus F is B1 carry. So A plus 1 plus 1 C, CB CCH. Then the ending address is CB CCH. Now one more memory is connected. So microprocessor is connected with external memory using address lines and data lines. In 8085 microprocessor, 16 address lines are there. These 16 address lines are connected like this. A0 to A12 is directly connected to the SRAM, and remaining address lines A13, A14, A15, these are connected to the one NAND gate. NAND gate output is connected to this one. Now this is a chip select here. Okay, now this is circuit. Then what is the range of this this memory locations? Memory address locations means here we have to find out starting address and ending address, right? So to find out the starting and ending address purpose, first we have to check this condition, how many address lines it requires. Just now we finished here 8 kilo. 8 kilo explains the 13 address lines. So 13 address lines are connected to this one. Okay, 13 address lines are connected to 8 kilo. So now A0 to A12 directly connected. And in microprocessor 16 address lines are there. Those 16 address lines are 13, 14, 15. Remaining 3 are connected to NAND gate. According to our diagram, your chip select bar is there. So if you want to use this memory, this chip select value should be 0 always required. Okay. See, memory activation purpose, chip select value should be 0. If it is 0, then only memory is activated, right? So when it becomes 0, if all the inputs of the NAND gate is 1 1 1 1, then only output is 0, right? So NAND gate is 1 1 1 means here I am taking A15, A14 and A13. These are connected to NAND gate. These lines should be 1 1 1. This line should be 1 1 1. Then only this NAND gate output is 0. Then the memory is activated. Okay. And again this memory is connected with 13 address lines. Right. So those 13 address lines explains the starting and ending address locations. So those address lines I am writing here. A12, next 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Right? These are directly connected. Directly connected locations are always, we have to take starting address is 0. So I am writing all are zeros. What is the ending address location? Ending address location should be 1. Okay, and these are same. There is no changes in that, because if these are 1 1 1 1, then only your memory is activated. That's why these 3 lines should be same operations, and remaining data is like this. Then connected to hexadecimal, 4 bits I am separating here. 4 bits are separated. Then the starting address location is, starting address is 1110. 110 is E000H, and ending address is FFH. Okay, so these type of questions are expected here. One memory starting address is mentioned, ending address is mentioned. From these two we have to find out starting address means number of address lines are connected. From these two we have to find out starting address and ending address, E00H2 FFFH according to the given memory. Now the same analysis, just small changes here. The changes are, here this NAND gate is connected with 3 inputs like this. Okay, some bubbles are given here. some bubbles are mentioned. Then the starting and ending address of the memory is, right? Just now I explained. Always we require this data should be 0, right? Because this is chip select bar. If it is 0, then only memory is activated. So 15 and 14, 13. These lines should be output of this should be 0 we require. For that purpose, NAND gate inputs are 1, 1, 1, 1. Then only your output is 0. Right? So when it becomes 1 here, so if A15 is 0 and A14 is 1 and A13 is 0. Okay? Only these combinations only. This NAND gate inputs are 1, 1, 1, 1. Then only output should be 0. Then your memory is activated. Okay? And remaining address lines. How many address lines? So 12, A12, next A11, A10, 9, 3, 2, 1, 0. These are used to find the starting address. Starting address is always 0. Write with 0, 0, 0, 0. Ending address is 1. Write with your 1, 1, 1, 1 combination. Okay. Then I want interest of hexadecimal format. That's why I'm converting into hexadecimal format. Hexadecimal format. Okay. 4 bits are separated. Then what is starting address location? 0, 1, 0, 0. Starting address is 0, 1, 0, 0 is 4, 0, 0, 0, H. Ending address 0, 1, 0, 1, 5. Ending address is 5. And these are 1, 1, 1, right? So F, 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 H. Okay. So this is another problem, starting address. And now same SRAM, 8 kilobyte 8 SRAM is connected with chip select is connected with one decoder. See, decoder inputs are 15, 14, 13. See, inputs are mentioned here A, B, C. See, always you have to assume this MSB is A and C is LSB, right? Sometimes your expected question is interchanging also. Sometimes 13 is connected here, 14, next 15. Then we have to take A is MSB. A is MSB means your 13 is MSB. 14, next 15. So according to the given decoder, you have to take that part, right? And any decoder internally enable is there. Enable is 1 here because this is active high pin. If it is active low pin, enable pin should be 0. So depends on the your type of the line, then this should be 0 or 1. And we want decoder should be active position. So here I connected with the active high pin. This should be 1. And from this, let us assume this third line is connected to the chip select. See, all these are active low outputs. Active low outputs means according to the input combinations, at a time only one output should be 0. At a time only one output should be 0. Now according to our connection, which output we require 0? Third line. So third line means your ABC locations. A, B, C. 0, 0, 0, it selects the D0. 0, 0, 1, D1. 0, 1, 0, 2. 0, 1, 1, 3. Like this is general decoder operation I am writing here. 5. 1, 1, 0, 6. 1, 1, 1, 7. Now we want this line. This line purpose, the status of the ABC is 0, 1, 1, 1. So I am writing 15, 14, 13 lines. What is the status? 0, 1, 1, 1. It has to maintain same. Then the remaining are used to find the actual address location. 12, 11, 10 up to 0. Next, all these are zeros. All these are zeros. Starting address. Ending address is all these are ones. Right? Now find starting address. 4 bits are separated, right? So 4 digits are separated. 0110. So your starting address is 01106000H and ending address is 01117FFFH. Okay, these are the starting and ending address locations. So in this memory interfacing, always we have to remember this chip select bar should be 0. This device is any device, any gate we can use here, either decoder, NAND gate, NOR gate, any type of gates. Output we want always 0 here. Okay, from the given circuit diagram, find out the input combinations. With those input combinations, our output should be 0. Then the memory is activated. Right? So this is the procedure to find the starting and the ending address locations of the memory. Okay. And in this another expected type question is finding number of ICs. So general formula is number of ICs required is required size upon available size. Okay, one example I am explaining here. That example is number of 256 by 8 ICs are required to design 8 kilo by 8 SRAM. See, this is our question now. To design 8 kilo by 8 SRAM purpose, how many number of these ICs are required? Right? So according to our given formula, number of ICs is required size. Required size is 8 kilo. This 8 kilo I am writing in terms of 2 power n representation, 2 power 3 by available size. Available size is 256. 256 in terms of 2 power 8, 2 power 3. Now, okay, now so cancel that one. According to the given combination, this one is cancelled. Later here 2 power 8 and here 2 power 13 is there. Then the result is 2 power 5. Okay, result is now 2 power 5. If it is 2 power 5, what is the data? 32. So how many ICs are required? 32 ICs are required. Okay, number of ICs required to design another IC. So this is the one standard formula. Number of ICs is equal to required size by available size. Right? So from that we can find here number of ICs like this, and these ICs are connected rows and column wise. That is depends on our convenient. 32 ICs, right? 32 ICs are 8 rows, 4 columns we can connect. Otherwise 4 rows and 8 columns. So 8 4 32. So the arrangement of the ICs is any order we can take. But the total number of ICs required is 32. This is another type of question expected from the memories here. Okay. So one type of question is finding starting and ending addresses. Okay. And another is finding number of address lines and number of data lines. Right? And another is from this given circuit diagram, starting and ending addresses. Later, finding number of integrated circuits to design another ICs. So these are the expected questions from microprocessor and interfacing.